You already know my name. I talk to you from Berlin, where I work for Wire. It's an end-to-end encrypted messenger. And I work in the Android team. In Wire, we use Scala on Android, and the backend is in Haskell. The, mm, the application is a bit unique among other Android application because it's written in 2/3 in Scala instead of Kotlin and Java, as would be more usual. And well, Wire is a messenger, so it has to be very responsive. It has to quickly react to any events coming from the backend, as well from the user, and as well from the Android. And for that, the Android team written this Wire Signals open source library with event streams and signals, which are like a build-up on top of event streams. There will be also some drawings of cats during the presentation because this is a video and I needed something to help me pace how I talk while the video is going on. Sorry for that. We will be talking about a bit about theory, about practice, and a bit about that open source library, which is not really an alternative to bigger projects like Akka, Monix, RxJava, or Live Data on Android. But it's like a very small thing that you can start with and maybe then move to something bigger, or just stay with it if your resources are limited, or just this is exactly what you need. So the theory behind event streams is that we basically talk about the observer pattern. You can read all about it in this old book by the so-called Gang of Four. The idea behind the observer pattern is to solve two problems. How can a one-to-many dependency between objects be defined without making the objects tightly coupled? And how can an object notify an open-ended number of other objects? And open-ended meaning that we don't know how many of them are there, and new ones can pop up at any moment. The main object here is called a producer or a subject. It's the source of events. And the other objects are called observers, but they are also known as listeners or subscribers. The terminology is a bit liberal. Some people may even argue that there are differences between those terms, but I think the main reason is that the pattern is with us for a long, long time, and it was implemented in a few various ways. So I will be calling them event stream for the producer and subscribers. And we will be talking about real producers for a moment, but a bit later. The event stream can produce or maybe broadcast an event at any moment. If there are no subscribers present, the event will be wasted. We may say that the event stream does not have an internal state. It does not store the event for the future use. It just broadcasts it and then forgets about it. But that wouldn't be entirely true. The event stream needs to store the set of references to the subscribers. So the set is empty at first, but then any object in the app which fulfills the criteria of being a subscriber can be added to it. So criteria being that it can receive an event of the given type. An event can be any piece of data. The subscriber is added to the set, and from now on, every time the event stream broadcasts a new event, the subscriber will receive it. There can be, of course, more than one subscriber. The event will then send to, the event stream will send events to all of them. And to finish receiving events, the subscriber needs to unsubscribe. The fact that it has to be explicit that the subscriber unsubscribes is a bit of a drawback here. In a complex application, for example, the programmer may forget that to call it when the subscriber is destroyed or when it's not any longer used. And in JVM, it may lead to a memory leak. Well, the garbage collector will not be able to collect the subscriber because there will still be the defunct reference. We can solve it. We can, for example, model subscriptions as case classes holding references to both the subscriber and the event stream and use it to unsubscribe in some sort of on-stop methods. Or we can use event context, that is implicit objects that will oversee subscriptions. But we don't have time to talk about it much now. I can talk about it later in the QA section. But where the events come from? In the original observer pattern, we assume that event stream is also the producer of events. It's even there in the book that we solve a problem of one-to-many dependency. We have one producer that somehow creates the data and sends it away. But these are really two operations, so we can decouple them. We can have a producer that is any part of application, and that producer gives data to event stream, which sends it to subscribers. And now, since the producer is separate from the event stream, then nothing is really preventing us from having more than one producer. The connection between event stream and subscribers and producers becomes many-to-many, with the event stream just sitting in the middle. This way, producers and subscribers don't have to know about each other. They only have to know about the event stream that operates on data of the given type. But in contrast to subscribers, producers don't even have to register in the event stream. For example, let's say our producer is an OK HTTP client. OK HTTP is an HTTP client library. It's very often used on Android. And let's say we have an instance of it, and we open a WebSocket that is a connection to the backend, and we wait for some data from it. So we don't actually produce anything, but from the point of view of our Android application, well, this is how data appears out of nowhere, out of thin air. Yeah, so we can model the subscriber as a trait and implement it like this. But forcing every class to extend subscriber to enable it to receive events is kind of verbose, when we can do better. We can actually use a for each method that will take a function and create a subscriber itself and add that subscriber to the set of subscribers. And yeah, and I would like to also introduce this small exclamation mark operator that is just a shorthand for the publish. Yeah, and this is enough then in the service that we can receive the message, and for example, this is how we can use it to display the message in the message view. But at this point, you might have thought that the subscriber trait here is a one method trait, and so we could just turn it into a function. Well, I'm usually for it. If our trait turns out to have only one method, I think it means we should really think about turning it into a function. But there's a reason why I didn't do it, but also let's talk about it in a moment. First, transformations. If broadcasting events was all an event trait could do, it wouldn't really be that interesting. Often subscribers either want to transform the event somehow before using it, and many subscribers may want to transform the event in the same way, or they are interested only in a certain subset of events coming from the event stream, or both. Or the logic can be even more complicated. For example, the event can be interesting to the subscriber only if a certain event from another source was received before, so we can use the flat map for this. And to address those needs, event stream implementations come with a long list of methods such as this, like map, collect, zip, filter, flat map. And with them, we can move the logic, which would otherwise have to be implemented in the subscriber. We can move that logic to the event stream. And each of that methods creates a new event stream, which the original event stream has as its producer of events. So map will transform the event into another event. Filter will publish the event only if certain condition is fulfilled. you may notice how all those methods are basically the same as in case of standard collections. Well, we can treat actually an event stream as a collection. You can think of it like there's an option in the standard collections, and future is a form of an option for the asynchronous computations. And a collection that can have only 1 or 0 elements, and depending on the computation, the future can be successful or not. And this similar correlation is between a sequence in the standard collections and event streams. And because event stream is a collection and it has a flat map, then we can use 4 comprehensions like this. And this is equivalent to code like this, which is a bit less readable, although it might not look like it because the example here is very simple. But imagine like a whole list of consecutive statements, transformations. It's based on some of the ones executed above, but also on other data. So here you can just read it one line after another, like the composition of many, many event streams. Threads. A moment ago, I skipped over one important issue. I said that the subscriber waits for an event coming from the event stream. But waiting means something different depending on if we talk about only one thread, like working on one thread, or with 2 or more. Like, let's consider this simple example. If the code works on only one thread, we will create a stream in the first line, subscribe to it in the second, and then just after publishing hello world in the third line to the event stream, the control will come back to the second line. The print line will display the hello world, and only then we will finish the method. But that's not how modern programs work, right? In Android, for example, it's customary that we work with at least 2 threads belonging to separate execution contexts, UI and background. The UI thread should be used only to display and refresh things on the screen. If our code does not touch the UI directly, it should work on the background thread. So if we have a list of items like here, and we want to display them, we display them on the UI thread. But to retrieve those lists from the storage, we should use and update them. We should use the background thread. So you can see the problem. If we don't have a way to differentiate between UI and background, then when an update happens to the storage, the for each method here, and consequently also update items on the screen will be called on the same thread. Fortunately, event streams are exactly the tool we need to jump from one thread to another with little ceremony, little problem. And that for each method will help us because it's a bit special and different. It's different from the other like map and flat map in one detail. And that is that it takes the execution context as its implicit parameter. In event streams, we can differentiate between the execution context of the source and the execution context of the subscriber. We can implement the for each so that it will take that execution context, it will create the subscriber and store the reference to the execution context in it. And then when the event comes, instead of just calling publishing it immediately, it can wrap the event and the function that will publish the event, it can wrap it in the future and call it on the execution context of the subscriber. And this way, even though the update items on the background thread are called in the background execution context, then this adapter.update items on the UI thread will be called in the UI thread just later. Of course, there's a special case when the execution context can be the same in both cases. We don't really need to use event streams only to talk between threads. But even then, I would rather say that this should be the default implementation. We can just call the publish the event inside the future, so we don't know exactly when it will happen, when we will receive the event. But this is more consistent with the same situation when we talk about different threads. So like our consistency in that we don't know the same things, even no matter if we work on one thread or on many. But of course, we can also implement a special case when the current execution context is the same as the one of the subscriber. This should be a special case. All right. I'm aware that it doesn't really answer the question why the subscriber trait cannot be a function, because, well, it's a bit more complicated than just a trivial implementation, but it's still possible, and I think I would like to do it. It's just that this code is a bit not easy to change. I need more time to work on it. If you think you can help me in a way by even if you want to just brainstorm a bit, please reach out, and or maybe like help me with unit test or anything. So okay, signals. Finally, a signal is not a commonly agreed name like an event stream. It's not an implementation of a popular pattern. Just that event streams are an implementation of the observer pattern, but it is a pattern, and it's a pattern that came up out of necessity in my work, and it developed quite naturally. So we implemented it, we tested it, we used it in several places in our code, even though arguably in the same application all the time. And finally, we moved it to a separate open source library and documented everything. In the same time, Android came up with live data, which is a very similar concept, but it's more tied to Android, while signals are platform independent, well, as long as that platform is Scala. Okay, what is a signal? In short, a signal is an event stream with a cache, and that's all. It's a very simple, small distinction, but it's also a very powerful one. Whereas an event stream holds no internal state except for the collection of subscribers and just passes an event it receives, a signal keeps the last value it received. A new subscriber function registered in an event stream will be called only when a new event is published, but a function registered in a signal will be called immediately or as soon as possible in the given execution context, and it will be called with the current value of the signal, unless the signal is not initialized yet. And then again, it will be called when the value changes. A signal is also able to compare a new value published in it with the old one. The new value will be passed only if it is different. And thus, a signal can help us with optimizing performance on both ends as a cache for values which otherwise would require expensive computations to produce them every time we need them, and as a way to ensure that subscriber functions are called only when the value actually changes, but not when the result of the intermediate computation is the same as before. You can think of it as of traffic lights. You're the driver, you come to the crossroads and check the traffic lights. That means you subscribe to them, but also you immediately get the current value and can act on it. If it's green, you go. If it's red or yellow, you stop and wait for a change. So one advantage is that in some cases, you don't have to wait. If it was an event stream, you would have to stop each time and wait until a new event would tell you it's safe to go. But there's also another advantage in that if, for any reason, the lights compute their value and that value is the same as before, then no new event comes, like no value does not change. In that case, for you, it's completely transparent that anything was computed. You wait for a different value, not the same value but computed again. The second example, of course, is quite unrealistic if we talk about traffic lights, but consider this. Say we want to perform some complex computations only if the value of the signal is even. let's assume, like for the sake of argument, that we actually don't have to perform complex computations every single time, but only if the value of the signal becomes even initially, or if it changes from odd to even later on. As we can see here, in this case, the complex computations are also performed when the value changes from one even number to another even number. Let's say it's not invalid. Let's say the result is the same as before. We only waste some CPU time with this. But we can do better. We can change this signal implementation to a new signal of the map, that is a signal of a Boolean value, and the for each of that signal will be called only if the Boolean changes and becomes true, that is, if the original number value becomes even from being odd previously or from an empty initialized signal. But if the number changes from one even number to another even number, then the value of the mapped signal just stays the same. It stays true, so the for each is not called at all. And this way, we just don't have to perform complex computations when it's not necessary. And I think with this, I will finish the talk. I will stay here, of course, for any questions. You can also go to GitHub and check the wire signals library yourself. You can read a bit of the documentation. And if you want to just test it, you can also just add it to dependencies. Thank you very much. You can also always find me on Twitter.